Hello and welcome to Civil Engineering Mathematics A. My name is Eric Tune and I'm a lecturer in mathematics at Central TAFE. This is program 5. Well, in this program we continue with algebra. In the previous program we looked at types of numbers, we looked at signed numbers, and we looked at algebraic expressions. Now we're going to work with these algebraic expressions, and in fact towards the end of this program we already will do some quite interesting applications of algebra. Well, let's have a look what exactly will be covered in this program. First thing we're going to do is substitution. Then we look at simplifying expressions. Removing brackets is next. Linear equations, they're quite important, and then word problems, and they can become quite difficult. Well, let's look at that first topic then, substitution. You have to know your algebraic rules before you can do substitution. Substitution is very important in engineering because you come across lots of formulae and you have to put values in those formulae. If you can't substitute in simple algebraic expressions, you will find that process very difficult in engineering. Let's have a look at what substitution is. We substitute a value. That means we assign a variable, we assign a value to a variable, and so we can then evaluate the literal expression. Let's have a look at an example. I've got minus 3x plus 1. That becomes minus 2 or negative 2 when x is equal to 1. It becomes a different value when x is equal to 0. It in fact becomes 1, and again a different value when x is equal to negative 2. So you have to know those rules. See that negative 2 times the negative 3, that becomes a positive 6, add a 1, and then you get the 7. Let's have a look at some problems, an easy one first and then a more difficult one. Evaluate those two expressions. First of all, 2x squared minus 4 for x equals minus 6. Well, here we go. We substitute the minus 6 in for the x, and we square the minus 6. If you square the minus 6, you get 36. So in the end we get 2 times 36, subtract 4 equals 68. The next expression, two different values there, x is 2 and y is negative 3. And when you substitute that in, you get a negative, or subtract 5 times negative 3, that becomes positive 15. And 2 plus 15 plus 6 is of course equal to 23. The next topic is about simplifying expressions, but before we can do that we have to know something about the terminology involved. There is in fact a lot of terminology involved with algebra. Like terms, for instance, is one of those. Let's have a look. A literal expression such as negative 3x squared y has one term. It's called a monomial. Just think of monorail. If it's got two terms, it's called a binomial. Now, an expression such that minus 3x squared y in fact has two parts to it. It's got a numerical coefficient, that negative 3, and it's got a literal coefficient. Now, as soon as the literal coefficient is the same in two expressions, you can talk about like terms. And what we can do with like terms is to add and subtract. In fact, that is the golden rule of algebra. Only like terms can be added or subtracted. I've got quite a nice example here why that is. We've got, for instance, dollars to stand D for dollars and C for cents. And if I receive $2 and then $3, in total I've received $5. So we can say $2 plus $3 equals $5. See, we keep that same letter part, but we add those 2 and 3's up to get a 5. Now, if you receive $2 and then 10 cents, you can't do much with it. You have to write it as $2 plus 10 cents. You can't simplify that and make that 20DC or whatever. It is 2D plus 10C. So this leads then to that important rule of algebra about simplifying expressions. Only like terms can be added or subtracted. It will come up on the screen now. I've called it rule 1. And when you add or subtract, what you have to do is you have to keep the same literal coefficient and you have to add or subtract the numerical coefficient. Let's have a look at an example as usual. Easy example first and then a more difficult one. 2D plus 10C plus 3D equals, let's look at problem A, Well, we can of course add the 2d to the 3d to get 5d, but we can't do anything more, and we leave that as 10c. In the next problem, 3x minus 5xy minus 2x plus 7xy plus 4. There is a 3x and a minus 2x. I can combine that. I can combine those two there. Can't do anything with the 4. And so the final simplification is x plus 2xy plus 4. When algebraic expressions are multiplied or divided, then you can get a different term. I've got that written down as rule 2. Multiplication or division of algebraic terms produces terms with a different literal coefficient. Let's look straight away at an example of that. I've got 2d times 10c in problem A. Well, I can split up the 2d as 2 times d and to change the d with the 10, because I can always say 3 times 5 is 5 times 3. So multiplication can always be interchanged. Then the answer becomes 20dc. See, I've got a new literal coefficient there out of d multiplied by c. Slightly more difficult problem with division. I can certainly divide the negative 30 by the negative 5 to give me 6. It's an x to the power of 4 divided by an x. That would give me x to the power of 3. And then the answer becomes 6x cubed. Now, brackets are always encountered in algebraic expressions, and you have to be aware how to simplify those. I've got it illustrated by means of an area calculation. See if you can follow this. I hope so. If I had to calculate the area of this triangle or this rectangle, I could multiply 5 by 3 to get 15, but I would not quite know what this area is. It would be 5 times whatever x is. Now, if I write that down algebraically, then I can say the area is 5 times x plus 5 times 3. 5 times 3 is 15, so I can write it as 5x plus 15. But I could have also done the multiplication by taking 5 and multiplying it direct by x plus 3. And therefore, those two expressions must be the same. So what you see is that that 5 is actually distributed among the x and among the 3 to produce 5x plus 15. Now formally, that's written down in the rule with A, B, and C, etc., and that's what we've got on the screen coming up. And we're using those letters then, AB plus AC. It's officially called the distributive property. When you have negative numbers, then of course that's going to affect things. If it's a negative 1 in front of these brackets, that's really a negative 1. We don't write that negative 1, we just write a negative sign, but that distributes as well, so it becomes negative b and then negative c. Also, when we've got a negative b minus c, it becomes a negative b, but that negative makes that one positive, and so we get negative b plus c. In fact, what we say with brackets, if there's a negative in front of the bracket, then every term inside the bracket changes sign. Let's look at some problems again. Here are the problems. Simplify, remove brackets and simplify. 3x plus 2 brackets x take away y. Take away 5, sorry. So we've got 3x, leave it like that, 2 times x, and then 2 times negative 5. That produces 2x, take away 10. We can now simplify the 3x and the 2x to make it 5x. That's the final answer. For the second one, a lot of negatives there. That will change all these signs there. So simplifying it, we get negative 6x, we get plus 3y, carry the 3 through. Then negative 2x, that changes the sign to a negative, becomes 14y plus 8. Then we combine all these terms together into negative 8x, subtract 11y plus 8. You've now been introduced to a variety of algebraic techniques and operations, but you have to practice that. You have to be really competent at it. In your book there are plenty of exercises on elementary algebra. Please go to your book and practice. Now after the break we come back with one of the more important applications of algebra, solving linear equations. In engineering we frequently encounter situations where we have to solve for an unknown value to work out, for instance, the strength of a beam. What we do is we let that unknown value be x and solve a problem. Now we can only solve very simple problems called linear equations. An equation, in fact, is a statement with an is equal in it, and a linear equation hasn't got any powers like squares or square roots. That's what I've got on the screen here. A linear equation, an equation is a statement with an equality sign, and a linear equation hasn't got any powers. It can be written in the form ax plus b. The highest power, we say, is equal to 1. Well, let's see how that works in some problems. Can we actually find whether these equations are linear or not? Well, the first one certainly is. There is no higher power of 1 involved. It's just 2 times x to the power of 1, so it's linear, with in fact the value a being 2 and b equals 7 in that previous formula. But the second one, you see the highest power there is a 2, so that's what's called a quadratic. We can't solve those as yet, but one day we will. X equals 7 doesn't look like one of those linear equations, but it certainly is an unusual situation. And then the next one, the square root of x plus 7 equals 0. Well, the square root of x, later we will learn that that is the same as x to the power and half, so that is not 1. Consequently, it is not a linear equation. Now, how do we solve linear equations? There are basically 2 techniques involved. First one is called cross multiplication. The next one is called transposition. I've got an illustration example of this first technique called cross multiplication. Let's see if you can follow this. Let x be the cost of an ice cream. If 5 ice creams cost $4.50, then 5x equals $4.50, or x equals $4.50 divided by 5. I'm actually not interested in the answer. But you see what happens. The 5 is multiplied by x. To get an answer, I divide by 5. This is a little bit more general. That 5 ice creams cost C dollars, then 5x equals C dollars, or x equals C dollars divided by 5. And in fact, I can buy any number of ice creams, A ice creams, that cost C dollars, then it's the same process. So x is equal to C dollars over A. Now that brings us to the general rule which I've got written up next. That is called the cross multiplication rule, coming up right now. If AX equals C, then X is C on A. So it's a multiplication, it becomes a division. Just illustrated earlier with these ice creams. So what we actually do is crossing on the is equal sign. You know, you cross like this. And that's what we've got written down here. See, that's that cross multiplication. Well, as usual, we're going to have some problems on that. Let's have a look. Cross multiplication problem. We've got solve 5x plus 10, and we've got negative x on 3 equals 6. Well, the first problem, we cross the 5 over, and then obviously we get x equals 10 divided by 5 equals 2. For the next problem, we cross the 3 over to make it 18. Slight complication because we're going to get negative x equals 18. We want the answer as x equals, so we change and divide by negative 1 to get negative 18. Now, you can always check by substitution that you've done that correctly, because if you substitute negative 18 into that equation, you got a negative and a negative that make a positive. 18 on 3 equals 6. Now, the other technique, there were 2, remember, cross multiplication. The other one is called transposition, and also a very important one. In short, it says change sides, change signs. Let's see how that works. I've got an example here, again, with ice creams. Well, actually, let the cost be of an ice cream. If you add $5 to that, then and the total is $5.90, then you can write that mathematically as x plus $5 equals $5.90, but then x is going to be equal to $5.90 minus $5.90. In general, of course, if we use p and q, you get this equation. X plus p dollars equals q dollars, then x is the difference between q dollars and p dollars. Now, if we write that in terms of a general rule, we get the following. Second rule, if x plus q equals p, then x is p minus q. And also, if x minus q equals p, then x equals p plus q. Now what happens? Have a look. If I have a plus q there and I want x on its own, I can bring that q to the other side, it becomes a negative q. If it's a negative q, I can bring it to the other side, it becomes positive q. We call that a transposition. And here we've got it. Change sides, change signs. Well, as usual, let's have a look at a few problems, how that works in practice. Transposing problems. Solve x minus 3 equals 7. First of all, bring the negative 3 to the other side, becomes positive 3, sorry, and that becomes a total of 10. You can always check by substitution, 10 minus 3 equals 7. And the next problem, 6 minus x equals 11, and then of course 6 minus 11 equals x. Consequently, negative 5 equals x, or minus 5 equals x, or x equals minus 5. And again, check by substitution. Now, what needs to be done first? If you have a situation where you have to do cross multiplication and transposition, well, there are some rules there, and I'll go quickly through those. Let's have a look. Rule 3, I can call it. You should really transpose first before cross multiplication. And I've got another rule on the screen here. Bring like terms together. Time for an example straight away. If you have to solve the following equations, 2x plus 3 equals 7, then what do you have to do? Well, like I said before, 2x plus 3 equals 7. Do the transposing first to make it 2x equals 4. Then do the cross multiplication. So divide 4 by 2 to get 2. Second problem, 6 take away x equals 21 plus 5x. Transpose first. Put the x's to one side, the numbers to the other side, and so we get a total of negative 6x equals 15. Then we divide 15 by negative 6, and we get negative 2.5. There are two other rules I want to briefly mention. The first one deals with brackets, the next one deals with fractions. Let's first of all look at the one about brackets. Rule 5. It says if you have brackets, you should really get rid of them at the beginning. Remove them at the beginning. The rule about the fraction goes like this. When you see fractions, try multiplying by the LCD. Now that stands for lowest common denominator. I think this is best illustrated by examples. Here we've got an example with brackets there. 2 brackets x plus 3 equals 7. First of all, we remove the brackets by multiplying the 2 by x and the 2 by the 3 to get 2x plus 6 equals 7. And then we solve in the normal manner. 2x equals 7, take away 6 by means of transposing, so 2x equals 1, x must be in half. The second problem, you see a 2 there in the bottom. That is called the lowest common denominator. If I multiply this whole part by 2 and that whole part by 2, I remove the fraction. Here we go. The lowest common denominator is 2, so I put 2 in front. I get 2 lots of x over 2. Well, that's simply equal to x because the 2 cancels against the 2. The 2 times 1 equals 2. And finally, the 2 times the negative 2 gives me negative 4. I'm back to one of those familiar equations. X plus 2 equals negative 4 means x equals negative 6. So far we've covered some very easy problems. Let's finish this section with a slightly more difficult one. I hope you can follow it. Here we've got 2x, take away 1 over 2 plus 3 equals negative 2 on 3 times x plus 2. So we have to do the brackets. First of all, however, I see a 2 and a 3, which is called the lowest common denominator, 6. I'll multiply everything by 6. If I do that, I will end up with 3 brackets 2x take 1 plus 18, remember it's 6 times 3 equals, and then we get 6 lots of negative 2 on 3. Well, that's negative 4 brackets x plus 2. So I've gotten rid of the fraction signs there, very important. Next screen. I've got the same statements that I had before. Now I get rid of the brackets, multiplying through. Then I have to collect the terms because I've got 6x takes 3 plus 18. That can be combined in plus 15. Bring x's to one side, numbers to the other side. So I transpose. Negative 4x goes to that side, becomes positive 4x. And the 15 goes to the other side, becomes negative 15. Finally, simplifying that becomes 10x equals negative 23. And the last step is the cross multiplication. And the answer, therefore, is negative 2.3. Now, I hope you agree with me that is a very difficult problem, and you have to go through it step by step and practice from your book some of these problems. Well, after the break, we come back with word problems. In word problems, we have to form the equation from the information given. So there might be quite a lengthy sentence, and you have to extract the algebra from that. There's a procedure which I've indicated here on the next slide. The first step would be to determine the unknown quantity and choose a logical letter to represent it. I think that's quite important. A diagram also would help. Write the equation, then you solve the equation just like we've done before, and then lastly you have to give the answer using the correct units. That is very important. As usual, some examples, straight into it. Here we've got a fully loaded jet that prior to takeoff carries 160,000 kilograms of fuel, people and luggage. Now its weight is 325,000 kilograms. What is the empty plane's weight? Now, it's a lot of information there. How can we solve that problem? Well, we let the empty plane's weight be W, a logical letter, as I've said before. So we let that be W. Then we know that W plus the 660,000 must be equal to 325,000. Here I've got my equation. Then I solve that by transposition to get W equal 165,000, and then finally I put it in the correct units. The weight of the empty plane is 165,000 kilograms. That's a very straightforward problem, although you have to do a bit of thinking about it. The next problem is a little bit more difficult. Here Bill originally had $54 and saved $12 per month until he had $150. For how many months did he save? Well, we let the number of months be M, a logical letter. Then we get this equation, the $54 he had originally plus 12M, because every month he saves 12, so it's 12 times M, and the total he wants is 150. We get the linear equation. Transposition first, 12M is 150 minus 54, and that works out to 96. Divide finally 96 by 12 to get 8. Put the correct units down, in this case it's month, so Bill saved for 8 months. A little bit more difficult. The next problem, you really have to do some thinking. Here we go, problem number 3. In this problem we've got a rectangle that is twice as long as it is wide. The perimeter is 48 centimeters. Find the width and then the area. Here we deal with two letters, W for the width and A for the area. Let's have a look. What do we know? Well, we know that the length is 2 times the width, so I've got length equals 2W, but I also know that the perimeter is 48. Now, in terms of the perimeter formula for a rectangle, it's always 2 lots of length plus breadth, so in this case it becomes 2 lots of W plus 2W, which is 6W. So I get 48 equals 6W. From that, I can get, of course, what W is, the width, that's 8. Now, then, if you draw a little diagram, you can get the width as 8. We know that the length must be twice as long, so that's 16. Consequently, the area becomes 8 times 60 equals 128. There's just enough time for one more problem. Let's have a look. Problem 4. We've got the total takings at a football match is 195,390. Adults pay $22 and children $12. And there are 3 times as many adults. Let n be the number of children. Then we've got 12 times n, because n is the number of children. They pay $12, 3 times as many adults as children, so that's 3n. They pay 22. That comes to that amount. Simplify, that comes to 78. N equals 195,390. Divide through and give the answer, of course, in the correct units, 2,505 children. You will agree with me that you have to practice this work. Well, it's done in chapter 6 in your book. And please do as many problems as you can. I hope that you found this program useful. I'm looking forward to your company in program 6. Bye for now. Hello and welcome to Civil Engineering Mathematics A. My name is Eric Tune. I'm a lecturer in mathematics at the Central TAFE in Perth, West Australia, and I'll be your host for this series of 8 programs. Civil Engineering Mathematics A, or CE, Math A as we sometimes call it, is part of the Certificate 4 in Civil and Structural Drafting. Students who finish this particular certificate normally work as drafting assistants in engineering firms. You'll find, however, that a lot of students do this certificate as part of a diploma. To be able to do a diploma in engineering, you have to have this certificate behind you. And so Engineering Math A, or Civil Engineering Math A, is an integral part of any course in engineering, whether that's mining engineering, structural engineering, civil engineering, or even electronic engineering. Civil Engineering Math A has a lot in common, in fact, with a nationally recognized subject called Engineering Mathematics A. That's taught Australia-wide. In fact, there are many other subjects that are very similar to Civil Engineering Math A, and I've got those listed on the screen here. We've got that nationally recognized subject, EA002. It's also very similar to surveying and mining mathematics, laboratory mathematics, if you study that in TAFE. Even if you do some remedial mathematics, mathematics fundamentals, for instance, you'll find elements in common. And finally, environmental calculations. What is in this particular subject? Well, let's turn again to the screen. I've got that divided into 8 lessons, 8 programs. The first one will deal with measurement and mensuration. The second program deals again with measurement and mensuration. Mensuration, by the way, is the use of formulae in measurement. But in program 2 we'll make a start with geometry. In program 3 we talk about the geometry of triangles and quadrilaterals. And then in program 4 it is algebra, followed by more algebra in program 5. And in 6 we start with evaluating formulae. And in 7 it's straight line geometry straight line coordinate geometry, and in program 8 it is introduction to trigonometry. Now you notice that we've got these numbers in front of these units. They refer to National Vocational Mathematics Curriculum modules. Again, they are taught Australia-wide. Now, what do you need to succeed in this particular subject? Well, mathematics is a doing subject. You can't do the mathematics just by looking at a screen. What you need is a textbook, and you need to practice it. And the textbook is specifically written for this type of mathematics, the technical mathematics. It's by Blair Eldis and Keith Pentland. It's called Mathematics for Technicians. It's the 4th edition. And it is available from West One Information and Sales, and you see the telephone number there on the screen, 9229-5252. So if you need to obtain that book, then please give that number a call, and they'll give you some information how to get it. Apart from a textbook, to succeed in this subject you will need a calculator. Now initially simple scientific calculator will do. Later perhaps you might want to buy a graphics calculator. There are some important skills that you have to learn, and I've listed those again here on the screen. You have to be able to round numbers, and you use a calculator. You have to estimate an answer. You should always check what you have keyed in, very important. Know where your important keys are. And you have to be able to substitute numbers into a formula. The other thing is, if the instruction manual is very important. A lot of students tend to lose their instruction manual, and then they're lost. One calculator that is very useful for this subject is the Casio. Perhaps you can see that here. It's the Casio FX82TL. It's widely available. It's got all the important features we need for this subject, and those features again have listed on the screen. The important keys are bracket keys. I hope you can see those. They are over here. We need a power key to raise numbers to a power. That's in the corner over there. Degrees, to change between degrees and radians, we need that later on, perhaps not necessarily in this subject. Then there's a memory key, M plus here, and another one is a change of sign key, very important on this calculator, that has brackets with a minus in there. And an exponential key you see here at the bottom. Thus, you need a good quality calculator, scientific calculator. So what we've got a textbook, we've got a calculator, but of course you have to enroll as well. You have to, if you want to get official recognition for studying this subject, you have to be enrolled. There are assessment requirements, and your local college will be able to tell you what they are. Now, what will be the procedure for these 8 programs? We'll go through the material. I'll put some slides, as we call them, on the screen. There is a problem there, and you try to do that. If you are watching these programs on a tape, you can, of course, stop the tape and do the problem then. A bit more difficult when you watch these programs direct, but the problems are not that difficult. It's actually all introductory type mathematics. And with practice, you should be able to succeed. And we'll make a start with program 1 shortly. Let's make a start with program 1. Now, program 1 deals with measurement and mensuration. Mensuration is the use of formula in measurement. The content of program 1 is as follows. We've got metric units, can talk about that, conversions, then we look at some rounding, the theorem of Pythagoras, very important in area calculations you'll find later, and finally perimeter calculations. Well, let's make a start with that first topic in this program. It's about units, the metric unit system, Système International. They call it actually SI. And if you look at this, we have 7 basic units. One is length, that's the unit for that is a meter, symbol M. We've got mass, the unit for that is kilogram. Then time, that's measured in seconds. And the current, that is to do with electricity, is measured in amperes. Now, there are some other ones, but we don't really use those much at all. Now, the nice thing about the metric system is that all the units are related to these 7 basic units. For instance, if you talk about a Newton, then that can be expressed in a combination of those 7 basic units. There are also conversion factors that relate these units. For instance, kilo means 1,000. We already know that. But there are some other terms used in engineering that you should be familiar with. Let's have a look at those. If we look at some large prefixes, as they're called, then the first one we come across is tera, with a symbol T, capital T. There's a giga, and you might have heard of a hard disk drive that has, for instance, 20 gigabytes. 10 to the power of 6, that means a million, is mega. 10 to the power of 3 is kilo. 10 to the power of 2, hecto, not used very much, and a deca as well. Now, those are units for large measurements. Now, there are also units for very small measurements, and I've got those listed coming up. We've got pico, that is 1 over 10 to the power of 12. That is symbol P. We've got nano, so you could have something called a nanometer. Micro, and that symbol you see over there is mu, is pronounced mu. And then milli, we're all familiar with, that's 1,000th. And then there's a centi, 100th, not used very much in engineering. And then we've got a deci, and that's hardly ever used. There are some very specific units. When the metric system was introduced, people were worried about having to express things in terms of 1,000 kilo. We were familiar with the British ton, and so some units were introduced in the Australian metric system that are quite specific. For instance, we talk about a ton at 1,000 kilograms, and the abbreviation there is a small t, and notice the spelling. And hectare, to use with area measurements, that's equal to 10,000 square meters, or 100 meters by 100 meters. And finally, we also use a liter, which is the same as 1,000 cubic centimeters. And the abbreviation for liter is capital L. Now let's have a look how we can use these prefixes in conversion problems. And I've got a problem on the board, and hopefully before the answer is given you are already able to give the answer. Let's have a look how that works. First problem I've got on the board here, or on the screen, talking as a school teacher, as you notice on the board, we've got the screen here. Convert 102 kilometers to meters. Well, pretty straightforward, because we know, of course, that there are 1,000 meters in every kilometer. And so if we multiply 102 by 1,000, or 10 to the power of 3, we get the answer as 102,000 meters. Problem 2, a little bit more difficult, and that's the way it normally will go. We start with an easy problem and then get into the more difficult problems. Problem 2, convert 268.5 micrograms to grams. Now, a microgram is 1/1,000,000th of a gram. So we're going to get a number with a lot of zeros in front, because we're going to get a very small number. Here we go. The conversion factor is 1 over 10 to the power of 6. That's the same as dividing by 10 to the power of 6. And as you can see, you get lots of zeros, because when you divide by 10 to the power of 6, as in this problem, that decimal point you see over there has to move 6 places to the front. And you have to introduce these extra zeros to be able to place that decimal point. Let's have a look at a slightly more difficult problem. Here we go. We've got convert 10.5 square meters to centimeters squared. When you convert squared units or cubic units, there is going to be a slight difficulty. You can't just, multiply by 1,000. You have to take into account whether it's a squared unit or a cubic unit. Typical problem here. We've got 1 square meter as 100 centimeters times 100 centimeters, so I'm already changing to the squared there. So that's going to be 10,000 squared centimeters. And then finally we want to have 10.5 square meters, so that number there has to be multiplied by the 10.5 to obtain in the end 105,000 squared centimeters. And that's the same the way it works in problem 4. We've got in problem 4 how many gigaliters in 531 cubic meters. Now a cubic meter is actually 100 times 100 times 100 cubic centimeters, and that makes it 1,000,000 cubic centimeters. Why do I change it to cubic centimeters? Well, a cubic centimeter, 1,000 of those make 1 liter, so I get 1,000 liters. And that's not a bad thing to remember, that 1 cubic meter is equal to 1,000 liters. We want to know how many gigaliters there are. Well, we have to divide by 10 to the power of 9, because the giga is related to 10 to the power of 9. But we've got already 1,000 liters, so it's really divided by 10 to the power of 6. And finally, if you work that out on the calculator, you get 0.00. You got again the decimal point moving 6 places to the front. Quite a difficult problem, that one. You might have to look at that in more detail and practice those sorts of problems from your book. Okay, let's have a short break and then we come back with rounding. Rounding is very important. There are in fact 2 methods for rounding, and the first type of rounding is what's called decimal place rounding. I've got the rule here there. If you have to round, say, to 2 decimal places, then you look at the digit to the right of the second decimal place. If it's less than 5, you do not change it. If it's greater than 5, you increase it by 1. And you always make sure that the digit you round is an even one. And that is written out here. So let's have a look at an example. It's a lot easier than just to look at this rule. I've got some examples here. Round 37.987 to 2 decimal places. That 7 is more than 5. That makes that 8 and 9, as you can see. The next problem, we've got to the nearest 100th. That means 2 decimal places. That 4 is less than 5, so that 8 stays. And if we have a situation like here where we've got a 5 and we have to round to 3 decimal places, then we'll want to make that 1 7 there at the end and 1 8, so that the last digit is going to be an even 1. The other type of rounding involves significant figures. In fact, I can fill a whole program about significant figures. It's perhaps best illustrated by means of some examples. I've got an example here where you're asked to find how many significant figures there are in 379087. Now, there are 6 significant figures. You just count how many figures there are. In the next one, that 0 is used to count people, so there are exactly 35,840 people. There are 5 significant figures in that measurement. In the next one, that decimal point there and those zeros, they are used to place the decimal point in position. They have nothing to do with the accuracy of the measurement, and so those zeros are not counted, and we actually end up with only 3 significant figures in that measurement. Very difficult topic, actually, significant figures. Let's have a look at another example. How many significant figures in 37.9 000 amperes. Those zeros at the end indicate an accuracy, and they are counted, and there are 6 significant figures there. In the next problem, we've got again those zeros involved. All of those are significant, so we should have 4 as an answer. But when it talks about approximations, then we only have 2, because that number really is rounded there. We've got 24,000 rounded, and so there are only 2 significant figures in that. You can see you really need your book to study this particular topic. Very difficult, actually, significant figures. The next topic is about the theorem of Pythagoras. That's a little easier. Let's have a look. What is the theorem of Pythagoras? You all have heard of that. When we've got a right-angled triangle, then the longer side, that is opposite the right angle, is called the hypotenuse. And when you square the hypotenuse, then you'll find that to be equal to the sum of the squares on those other 2 sides. Now, mathematically, that's expressed as BC squared is equal to AB squared plus AC squared. Sometimes it's written differently, because BC might be called little a because it's opposite angle A, and AB is called little b, and AC is called little c. So you might see it as A squared equals B squared plus C squared. Let's have a look at some typical problems involving the theorem of Pythagoras. The first problem here is where we want to find the hypotenuse, knowing those 2 other sides. We might have to do some rounding there. We have that the square on x is equal to 3 squared plus the 5 squared. Work that out to be 9 plus 25 or 34. Then you have to take the square root of 34, and you use your calculator, and then you round it to 2 decimal places, 5.83. Slightly more difficult problem here. Here the hypotenuse is known as 2.4, and we have to find that particular side, so we have to do a subtraction. When you do the subtraction, 5.2 squared, subtract 2.4 squared, put it in the calculator, make sure you use the brackets, and round it to the nearest meter in this particular case. That means 3 decimal places, because the units are kilometers. So this is really quite a difficult problem, as you can see. If the hypotenuse is given, indeed you have to do the subtraction. The next problem is more difficult even. There you will need some algebra, and of course we're going to do that later on in program 4. Here we've got a triangle That value there is x. We know that side is 5, that is 8 meters, and we know also that AB is equal to BC. Now, how do we go about it? We let that AB side be x, and then from Pythagoras we know that dA squared must be equal to 5 squared, the hypotenuse squared, minus x squared. But we also know in the big triangle that dA squared must be equal to the hypotenuse squared minus AC. Now AC is, if that is x and that's x, must be 2x. See, here we get into algebra. When you work that out, then here we've got those two equations. dA squared must be equal to dA squared. In other words, 25 minus x squared must be equal to 64 minus 4x squared. If you square that, you get 4x squared. You have to perform some algebra. You get 3x squared as 39, x squared as 13 as a result, and then we have to take the square root to get the value for dA, and if you do that, then you finally get 3.5. Very difficult problem just to follow on the screen like that. You need to practice, of course, from your textbook. Okay, let's have a short break and then we move on to our next topic, and that is about perimeters. The last topic in this program deals with perimeter calculations. Now, perimeter is simply the outside edge of a particular figure. Officially then, it's the distance traveled in moving once around the boundary. Now, for a circle, that perimeter is called the circumference. And it's got a special formula which you have seen before. It's pi, which is about 3.14 times the diameter. Let's get straight into a few problems, some easy ones first and then some more difficult ones. Easy one first. What is the perimeter of this rectangle? Well, if it's a rectangle, this side there must be equal there, so that's 6, that's 6, that's 4, that's 4. So it's going to be 2 lots of 4 and 2 lots of 6. And as we see, that equals 20 meters. Don't forget those units, because that is in units of meters. Then the answer must also be stated in meters. Let's go into problem 2, a little bit more difficult. Here we've got a circle with a radius of 3.5 centimeters. That means that the diameter is going to be 7 centimeters. So we multiply pi by 7. Pi, of course, you can get from the calculator. You should use the pi on the calculator rather than 3.14. Working that one out, it comes to 21.9911, and that goes on. We have to round, it says here, to 3 significant figures, so we want 1 decimal place, and it becomes 22.0 centimeters. Problem 3, we've got an interesting problem because not many people know that. We know that the equator is about 40,000 kilometers long. What is the radius of the Earth? In other words, if you want to dig from here to the center of the Earth, how far do you have to dig? We can work that out now using the formula. Here we go. We know that the circumference is pi times the diameter. We know that the circumference is 40,000. We can now work out what the diameter is by dividing 40,000 by pi. We get approximately 12,732. If you now halve that and round it correctly to 2 significant figures, you should get 6,400 kilometers. So that is the radius of the Earth, and that's how it is normally written, R with a little E at the bottom for Earth. In the last problem, we look at a so-called composite problem. Here we've got a trapezium. We can work out what the side there is by using Pythagoras, because if that's 3 meters, then that must be 3 meters. We've got that side as 4, so we know that the hypotenuse is 5, and then it's just a matter of adding 5 to 3 to 4 to 6 to get the perimeter as 18 meters. Careful again with those units. I hope that you agree with me that you have to practice problems of the type I've done here on the computer. The work is covered in chapter 3. Try to do all exercises up to the topic area. effect area will be covered in program 2. Well, I hope you found this program of interest. I'm looking forward to your company in program 2.